If you compress Earth's history into one dramatic story, trilobites are one of its longest-running lead characters. They were marine arthropods, part of a major animal lineage that includes modern crabs and insects, but trilobites belong to an ancient branch that no longer exists. Their name means three-lobed, describing the basic body layout seen in many fossils, a central axis with two side lobes. That sounds like a small anatomical detail, but it points to something bigger. Trilobites were not a single creature repeated through time. They were a huge class with over 22,000 described species, occupying many forms and habitats. They first appear in the fossil record roughly 521 million years ago, during the early Cambrian, and remain until about 251.9 million years ago. That span is close to 270 million years, far longer than most famous animal groups. To survive that long, trilobites had to do more than exist. They had to repeatedly adapt as oceans, climates, food webs, and entire marine communities changed around them. One reason trilobites are so central to paleontology is that they left behind an unusually rich fossil trail. Their exoskeletons were mineralized with calcite, which is much more likely to preserve than soft tissues. In marine settings where sediment accumulated, trilobite remains could be buried and fossilized in large numbers. This gave scientists not just isolated specimens, but repeated records across many rock layers and continents. That abundance matters because paleontology is often limited by patchy evidence. With trilobites, the evidence is dense enough to track evolutionary change in detail, shifting body forms, turnover of species, and expansion or contraction of lineages through time. Their fossils help reconstruct ancient environments and compare distant geologic formations. So trilobites are not only interesting organisms, they are also high-resolution data points. In practical terms, they became one of the best documented windows into early marine evolution, letting researchers test broad evolutionary patterns using a fossil group that is both diverse and consistently preserved. Trilobites are also crucial in biostratigraphy, the science of using fossils to date and correlate rock layers. If a particular trilobite species appears in two distant outcrops, geologists can infer those rocks formed during a similar interval. This turns trilobite fossils into time markers, helping build regional and even global geologic timelines. That has consequences far beyond naming species. It supports reconstructions of basin development, sea level shifts, and the movement of continents through plate tectonics. When crustal blocks drift and collide, rock sequences get separated, folded, and displaced. Fossil correlation helps reconnect those fragments into coherent history. Trilobites are especially useful because they were widespread, diverse, and evolutionarily dynamic, creating many diagnostic species through time. Their record effectively acts like a biological barcode system embedded in stone. Without fossil groups like trilobites, Earth history would be much harder to synchronize across regions. Their shells became tools for reading planetary change, linking biology with geology in a way few extinct groups can match. Even with abundant fossils, trilobite evolutionary relationships still hold open questions. They are placed within a broader clade called Archaeopodha, which includes several trilobite-like organisms. But many of those relatives had weaker mineralization or soft-bodied traits, meaning they fossilized less reliably. That creates a preservation bias. Trilobites can appear disproportionately dominant in the record partly because their shells survived better. Scientists must constantly account for this when reconstructing ancient ecosystems and phylogeny. The uncertain relationship between Archaeopodha and other major arthropod branches shows how deep time classification is both evidence-driven and provisional. New exceptional fossil sites can rapidly improve the picture by preserving anatomy normally lost. So trilobite research is not static cataloging, it is an active process of refining how major animal groups diverged. In that sense, trilobites teach two lessons at once. First, they were genuinely successful and widespread. Second, what we know about life's past is filtered through preservation. Understanding that filter is essential if we want realistic evolutionary narratives rather than fossil illusions. Ecologically, trilobites were far more versatile than the stereotype of simple bottom crawlers. Different species occupied different niches across ancient marine systems. Some moved over the seabed as predators or scavengers, feeding on smaller organisms or organic remains. Others likely filter-fed, processing suspended particles. Some forms swam and consumed plankton, using water column resources rather than relying only on benthic feeding. There is also evidence that most lifestyle categories seen in modern marine arthropods already had trilobite analogues, with parasitism being one debated exception. This breadth matters because ecological diversity often underpins long-term evolutionary persistence. If a group can exploit multiple food sources and habitats, environmental disruption in one niche does not immediately collapse the entire lineage. Certain trilobites, such as members of Alenidae, are even proposed to have had symbiotic relationships with sulfur-eating bacteria, potentially allowing survival in chemically unusual settings. Whether every detail of that hypothesis holds or not, it illustrates an important pattern. Trilobites were experimenters in ecological strategy, not locked into a single way of life. Their body size range reinforces that ecological complexity. Some trilobites were small and likely occupied low-level trophic positions or specialized microhabitats. Others were giants by Paleozoic standards, exceeding 70 centimeters and perhaps reaching around 4.5 kilograms. Size in evolutionary systems is never just a number. It intersects with predation, mobility, metabolism, reproduction, and habitat use. Larger trilobites may have benefited from stronger defense and access to broader prey options, while smaller forms could exploit narrow ecological spaces and potentially rebound faster under stress. The exoskeleton itself added another advantage: articulated armor balancing protection and flexibility. Instead of choosing between rigidity and movement, trilobites often had both. Over millions of years, this architectural platform could be modified into many functional designs, which helps explain the high species count. Their success was not about one perfect morphology but about evolvability, the ability of a body plan to generate useful variation. Trilobites show how a robust structural template can produce long-lived adaptive radiations when coupled with diverse ecological opportunities. The timing of trilobite expansion is as significant as their form. Soon after first appearing in the early Cambrian, they were already geographically dispersed and taxonomically diverse. That rapid establishment suggests either very fast early radiation or earlier undocumented origins in strata that remain unsampled or poorly preserved. By the late Cambrian and into the Ordovician, trilobites reached a major diversity apex. This interval coincides with broader marine diversification, when ecosystems became more layered and interactions more complex. Trilobites were not passive participants in that transition. Their abundance and variety indicate they were integral components of food webs and seafloor dynamics. Importantly, they remained diverse through the Silurian and early Devonian, meaning their rise was not a brief Cambrian burst followed by immediate decline. They had staying power. In macroevolutionary terms, that combination of early radiation and long persistence is rare. Many groups explode in diversity and fade quickly. Trilobites did the harder thing. They converted initial expansion into durable occupation of marine ecosystems over vast stretches of geologic time. Their decline, however, reveals how even resilient lineages can be eroded by repeated shocks. During the mid to late Devonian, trilobite diversity dropped sharply under successive extinction pressures, including the Taganic event, the Kellwasser crisis of the late Devonian mass extinction, and the Hangenberg event at the Devonian close. This sequence matters because serial disturbances can be more destructive over time than a single collapse. Each pulse removes species, narrows ecological range, and reduces geographic or functional redundancy. After enough attrition, the group may still exist but with diminished resilience. That appears to be what happened. Most trilobite orders were eliminated, and Proetida emerged as the only surviving order. Once diversity bottlenecks reach that level, evolutionary options contract. Fewer lineages means fewer experiments in adaptation, fewer buffers against change, and greater dependence on stable conditions. The trilobite story here is not sudden failure but cumulative vulnerability. Their eventual extinction starts long before the final event, built through repeated losses that progressively weakened one of Earth's most successful marine clades. After the Devonian crises, trilobites did show some recovery in the early Carboniferous, which is important because it proves they retained adaptive capacity. But the recovery was limited. Diversity never returned to earlier highs, and through the late Carboniferous and Permian they persisted at low levels even while remaining geographically widespread. That combination can mislead observers. Broad distribution may look healthy, but low diversity often signals fragility. If environmental change intensifies, a depauperate clade has fewer evolutionary pathways available. By the end of the Permian, trilobites were reduced to only a handful of species. Then came the end Permian mass extinction around 251.9 million years ago, the most severe biotic crisis in Earth history, and the remaining trilobites disappeared. It is crucial not to frame this as simple evolutionary inferiority. Trilobites had already proven exceptional resilience for hundreds of millions of years. Their final loss reflects compounded stress, long-term attrition from earlier crises plus terminal global disruption. They were not short-lived evolutionary experiments. They were veteran survivors overtaken by extraordinary planetary scale instability. Today, trilobites remain scientifically powerful because they support large-scale questions about evolution, extinction, and Earth systems. With such a long duration and dense fossil signal, researchers can examine how clades radiate, plateau, fragment, and vanish under varying environmental regimes. Trilobites help test whether ecological breadth predicts survivorship, how recovery unfolds after mass stress, and how repeated disturbances alter long-term trajectories. They also anchor geologic correlation, giving temporal precision to studies of sedimentary basins, sea level cycles, and continental reconfiguration. In short, trilobites function as both organisms and instruments. Philosophically, their history challenges linear ideas of progress. They were ancient, adaptable, and enormously successful, yet still mortal as a lineage. Evolution does not guarantee permanence. It continuously negotiates with changing environments. Trilobites embody that truth at epic scale. Their fossils are not just relics of vanished creatures but records of resilience, adaptation, and eventual vulnerability written across nearly 270 million years of ocean history, still shaping how we read life's deep past. If you found this helpful, please like this video and subscribe for more explainers.